Well, hello there again. Today we're going to have a look at the very interesting area of some conics. And the name comes from the fact that if you take a slice through a three-dimensional cone, then the cross-section you get is some of these shapes. You can get circles, ellipses, hyperbolae, parabolae, and it's just amazing. So anyway, without further ado, we're going to explore today ellipses and hyperbolae, and we're going to also reveal to you the shocking truth that circles are actually special cases of ellipses. Wow. So here we go. Now I want you to consider the equation x squared plus y squared equals r squared. So what is that shape? Yes, it is. It's a circle, and it has centre at the origin, and it has a radius of r. Now we're going to slightly rearrange that equation so that it looks a bit different to what you might be used to, as follows. That's pretty interesting. So we've divided both sides by r squared. Well, why would we do that? I can hear you asking, because you're not used to looking at it that way. Well, all will be revealed. Just be patient. Now, look at this. Good heavens. Now we've changed it so that we've got a and b on the denominators. In fact, a squared and b squared, and a is not necessarily equal to b. That frees us up to make a bent circle, where if a is not the same as b, you've got yourself a squashed circle or an ellipse. Good heavens above. So, let's see what I've written here. Yes. Now, this is now the equation of an ellipse where x squared over a squared plus y squared over b squared is equal to 1. The a squared term refers to a, where a is now what used to be the horizontal, if you like, radius of, if it was a circle, but it isn't a circle anymore. It's called the x semi-axis, or halfway across the horizontal at the widest point, and the b term is now the y semi-axis, which is halfway vertically at the widest point from the centre to either the top or the bottom. For a circle, of course, yes, a equals b equals r. So that's how it goes. Yes, there we have a little diagram for you, and a is the x semi-axis and b is the y semi-axis. Right. Good show. Now, we're going to generalise this now. What about if we change the centre of our ellipse from the origin to a point h and k? What would we get now? Well, stand by. Oh, wow, look at that. And we've got, straight out of the textbook, we've got that equation. And there it is. It's just exactly what I said, you see? We've got the centre of this ellipse is at h and k. A is the x semi-axis, b is the y semi-axis, and that's it. I think I've just summarised that for you. Yep, that's the centre. And yes, that's what a is the x semi-axis length, and y is the b is the y semi-axis length. So there's that, okay? So we're going well so far. There's a little diagram just to reinforce it for you. We've got h and k is the centre, and we've got, that's your a and that's your b. Okay. Ellipse is an oval or egg shape, a squashed circle. Yes, that's right. I'm sort of trying to equate it to the radius there, but you can't really use the term radius because it isn't a radius anymore, is it? Because it's not a circle. So, same thing with the y. Yeah, okay, so far so good. Let's move on. So if a equals b, yes, what is the shape? Yes, it is a circle. Okay, I think we've got that now. Let's keep going. Now, I've got two examples there which we are going to sketch the graphs of, okay? The first one is first, and the second one, we'll do that later. Now, that is an ellipse. That one there, as you can see, the centre is 2 and 3, A is 3, and B is 4. So this one is higher than it's wide. You can just read that, glean that from those numbers, okay? So what we've got to do is solve the thing and sketch it. Okay, well, what we need to do now is work out the intercepts. That's all important, of course, because we know the centre, we know the general shape. So let's go for the y-intercepts first. And that happens when x is 0. So there I am going, I've made x 0 from that equation on the left-hand side top. So the x term vanishes, and then you're left to solve it for y, okay? And that's what we're going to do now. Okay, I've multiplied both sides by 16, and that's what you get there. And now I've got to take the square root, and there it is, because 18 is 16 times 5, and that's where the 4 comes outside the square root sign as. And now finally I can get y is equal to 3 plus or minus that term, 4 root 5 over 3. So they are our y-intercepts. And I'm going to write them as intercept points because generally that's the way we have to express these things. And you'll note that I've put them in exact form, no decimals anywhere, okay? Don't do decimals unless you are asked, which you hardly ever will be in a question like this, okay? I think we've got to do the x-intercepts now. Oh, here we go. Now, they occur when y is 0. So we go through the whole routine again. Off we go. Now I've made the y term 0, and the same procedure, corresponding procedure. We're going to multiply both sides by 9, and that, I think that gets 63 over 16. However, I probably just want to leave it like that because I know that 9 is 3 squared, so the square root is, that 9 over 16 is just going to give me 3 over 4, so that's probably the best way to leave that. Oh, look at that. Beautiful. And therefore, I've just written the actual coordinate points there as our x-intercepts. Okay, now, I think that's everything now. We've just got to sketch the graph of it. Oh, look at that. Wow. So there it is. I actually did that on the calculator and then did a screen dump for you, okay? Alright, so just to reinforce the point, I'm going to write all the intercepts in there for you. Or there's the centre, and here comes the x-intercepts. Now, that left-hand x-intercept looks like the origin, but it isn't. It's just a very slightly negative value, if you care to work that out on your calculator. Now, here comes the y ones. Same thing with that intercept on the y, it's slightly negative. And here comes the other y-intercept. So there you are. There it is. And I'm just explaining there with that little note that that's not actually the origin, even though it looks very much like it, okay? Alright then. Now, let's do the second one. The thing I really want you to notice here is if you see an expression like that where you've got an x squared term and a y squared term, and the coefficients of them are different, that is an ellipse. If they're the same, yes, it's a circle, like what you've been used to up to this point, okay? That's how you tell. But they have to be both plus x squared and plus y squared terms. If they're not, if one of them's plus or one of them's minus, as we'll see later, that's actually not an ellipse, that becomes a hyperbola. Okay? Alright, now, what are we saying? Yes, that is an ellipse because of the coefficients being different. Okay, so in order to solve this particular equation, we're going to have to complete the square for x because there is a second x term there, a squared x term and a x to the 1 term, which means to get a linear factor out of that, we have to complete the square. The y squared term's alright, but not the x, so that's what we've got to do. So let's go for that. Okay, got it. Now, did you know how to do that? Hope you did, because you've got to take the 3 outside, both the x squared and the 24x term, and that's what it becomes in the bracket. If you're not sure, multiply it out again and have a look and see whether you're doing it correctly, okay? But if you multiply by something outside the bracket, you must divide by it inside the bracket to compensate. That's the way it goes. All right, next line. Yes, I need a 16, and I need to take 16 away straight away. Now I want to get rid of that negative 16, the last term in that first bracket, because it's no use to me in there. So here we're going to do that. But be careful, it comes out of the bracket as a negative 48. Don't make that error. Now we're nearly there now, I think. Let's just tidy that up. Aha, this is what we want. Now we're going to divide both sides by, yes, 12 to get it in the form we want it. And now we can see what we're doing, okay? So, you tell me, what is the centre? Did I hear you say negative 4 and 0? Yes. What is the A term? Yes, it's 2. And what is the B term? Yes, it's root 12. Or 2 root 3. That's what that comes to. And that's what we got. Now, it's up to us to... we have to work out the intercepts, of course. Yeah, now, what did I say the centre was? It was -4 and 0. Okay, so it's centrally located above the x-axis and the y-axis, so... that's not so difficult to work out in this case. I can tell you straight away what it is actually, because the A term was 4, so therefore that's the semi-axis, and therefore, yeah, you get that. It's easy to work out because you're going to get, I just forget now, but that's what you get anyway. Okay, so are you happy with that? I'm going to write the intercepts in, and the centre, just to reinforce the point for you. Write them as coordinate points unless asked otherwise. Always coordinate points. There you go. That was beautiful, wasn't it? Now we're going to do hyperbolae, and they are the most interesting beasts you've ever seen. And it's very similar to the equation of a circle and an ellipse, because these guys are all cousins. They're all conics. If you've got x squared over a squared minus y squared over b squared equals 1, or conversely y squared over b squared minus x squared over a squared equals 1, you got yourself a hyperbola, okay? Now, this particular version of it, where the x squared over a squared is the positive term, gives you that shape hyperbola, where you get x intercepts, okay? The next one, where you've got the y squared over b squared is the positive term, you get a different shape where everything else stays the same, but the hyperbola changes its position. The asymptotes remain the same, and the hyperbola becomes an up and down one. Okay, that's how that goes. But what you've got to remember is whichever the positive term is, that's the one that's got the intercepts, okay? That's the one that's got the intercepts. So this one here is the y squared term. That's got the intercepts. Okay? That's what I'm saying there, just to reinforce the point. Yes, sirree, babe. Now, we'll just go over the page now, and we'll do a real life one. Oh, no, I'm writing here, the asymptotes. Okay. So how do you work out the asymptotes? Well, you solve it for y, first of all, and then I'll show you a neat little trick. You solve for y to work out the asymptotes. There's the rigorous way, which we're going to do now. Then there's this quick and dirty way, which I'll show you, which you're really going to like. Okay, so what are we saying? Yeah, that's the first step to solving for y. Then we're going to basically multiply both sides by b squared and then take the square root. And I think I just did. Yeah, I did. There you go. Now, that's how it works. Now, for the asymptotes, as x gets larger and larger and larger, what's going to happen is that the two terms under the square root sign, the x is just going to take over in terms of its predominance, and the one term is just going to be absolutely piffling in comparison. So the trend is that it's trending closer and closer and closer and closer and closer to the fact where the 1 kind of doesn't make much difference at all. In fact, the 1 is just what keeps the hyperbola off the asymptote. And if you neglect the 1, you actually get the asymptote. That's the secret. So what I'm just trying to express that there. See, if you forget the 1, you get the asymptote. That's what you get. Although the curve never actually gets there itself, it's always kept off it by the smallest, thinnest, minuscule margin as x gets very large. The asymptote itself is what I've just written there. Now that's easy to take the square root of that term, and we'll go over the page and we'll continue our adventure. Now that becomes that's it. That's it. They're your two asymptotes, okay? Gradient is b over a. In that case, one of them's got a positive gradient and one of them's got a negative gradient. Alright, now, okay, they are the asymptotes, and you must work the equations out of those asymptotes, okay? Now, the easy way to solve and find the asymptotes is as follows. The quick and dirty way for the asymptotes is coming up. Now I'm going to use this example here where we've got x minus 2 all squared over 16 minus y plus 4 squared over 12 equals 1. Now you can immediately see that that is a hyperbola because of that minus sign in the middle. Okay, one's got to be plus and one's got to be minus. The centre is the point 2, negative 4. That is where the asymptotes meet. The A term is 4, and the B term doesn't have a direct little signpost here as to what's going on. It just affects the gradient of the asymptotes, okay? So, yes, it's a hyperbola, and it's that type because the x squared term is the positive one, and the centre is 2 and negative 4. Yes, it is. And the A, now see that A I've just put in red there, that A term, that is the distance from the centre, which is where the asymptotes meet, to the vertex of the hyperbola, okay? That is the distance. And it's the same on the other side of the of the centre, okay? That's something very important for you to get. Yeah, I've just highlighted that for you, okay? The a squared term is 16, therefore a is 4. So now you've immediately got the distance from the centre of the hyperbola to the vertex. Okay, now for the asymptotes, we've got, now you can solve that, you can neglect the one term. See how I crossed it up above there, crossed it off? I mean, you're strictly not allowed to do that, but we're just solving for the asymptotes. So in that case it is valid to just get rid of that one. So I've solved it for you. So there's the asymptotes. Now, obviously, that term under the square root is 3 over 4. If we go over the page. Yeah, just restating that. Now let's proceed. Yeah, that's what we've got. That's what we've got. Now, they're your asymptotes, okay? There they are. One's got a gradient of root 3 over 2, one's got a gradient of negative root 3 over 2, and they are centred at the point minus, 2 is the x and minus 4 is the y. That's right. There we go. That's where they cross, okay? Yeah, that's it. One's got a gradient of root 3 on 2, and the other one's got a gradient of minus root 3 on 2. My goodness, we're cooking along well here. Now, what else do we need to know? Oh, the intercepts. Okay, but there's a bit more information here for you. You do have to calculate the intercepts of the actual hyperbola. Yes, you do, and you have to write them in exact form, unless they tell you otherwise, which they never will. And you don't have to calculate the intercepts of the asymptotes. That's the x and y intercepts. However, the proportion and the gradient of the asymptotes has to be right, okay? You can't just mess it all up. So it might be that you actually have to calculate the intercepts just to get your proportions right, if you know what I mean, okay? But they don't require you to actually state them. And you don't give them any more information than what they ask for, by the way, because if you get something wrong, then you lose a mark somewhere. That's another hot tip for you. Okay, you have to mark all the intercepts on the graph in exact form. Yes, you do, unfortunately. And you have to mark both asymptotes with their equations, and you dot them and you label them. Okay, very important. Now, I've got to do a little hissy fit here on asymptotic behaviour. This is the bane of the examiner's existence, and you need to get this right. Okay, let me demonstrate. Here's a hyperbola coming up. Now, there's my two red dots for where it crosses the x-axis, and here's a hyperbola for you. Now I want you to look very closely at the way that black line, which is the hyperbola, is actually approaching the dotted line and never swings out away from it and doesn't really go parallel to it. And in that regard, please take a small plastic ruler into the exam with you and make sure the jolly thing approaches the asymptote as x increases. Okay, just make sure that there's no opportunity to lose your mark. Okay, now I'm just stating that down there for you. Always approaches the asymptotes as x gets bigger and bigger and you know, towards the plus direction and also the negative direction. Now, what we're going to do now is, yeah, they all get a tick because they're okay. Because I took my ruler, well actually I didn't, but you will into your exam room. Now, I'm going to do a really awful one now. Look at that. They're swinging away. They're swinging away like Halley's Comet, coming into Earth and going back out again as x gets bigger. That is completely wrong. Don't do that, okay? End of my hissy fit. Just don't do it. You will lose your mark. And so many students do. It's like fashionable or something. It's not fashionable in my book. Wow, Alakazam, there's our graph. There's our hyperbola. Look at it. It's pretty busy. So the black lines are the actual hyperbola itself, and the purple and green lines are the asymptotes. So I'm just going to put everything in there. It's going to look like a junkyard when we're finished. There's A. A was 4. So that tells you that that vertex is going to be 4x units to the right, and there it is. That's that term. And there's your centre, and 4x units to the left, by the way, as well, of the centre. Now, I've labelled each of the graphs as you are required to do. I should have dotted those, the purple and green ones, but you know the calculator that I used didn't do that, so you'll just have to excuse that. Oh, actually, I think you can. I just forgot, okay? So please don't you forget. Now what am I doing here? Yes. So what I've done is I've marked the vertices of the hyperbola. Now I've cunningly in the background worked out the x-intercepts of this monster, and there they are. My goodness, is there anything else I could do to junk this page up? No. There's my wow. There's stuff everywhere, isn't there? So there it is, okay? Pretty exciting stuff, really. Now, we have been using that particular hyperbola, okay, as the example. Now, here's the last little thing I want to show you. Whoa, there it is, okay? There it is. Just it materializes thanks to technology. Now, to summarize, the center is 2 and minus 4. There it is, written in for you. And what else have I got here? A is 4, so yeah, there, that's showing you that, and putting in the 4 on either side of the centre to wherever the vertices are, to where the curve just comes along that centre line. Okay. Now, yeah, there they are. Easy to work out in that case. Yeah, that's a vertex and that's a vertex. Now, what else have I got for you? Asymptotes, yeah, the asymptotes, I've just written them out there for you. That's what they are. And you can see that the equation of those asymptotes, in terms of your transformations, you take a centre on the origin, if you like, and you translate it by 2 units to the right and 4 units down. Right? That's how you do it. Yeah. Okay, now what about if y plus, oh yeah, this is the other kind of hyperbola. Now I've got the y squared term is the positive and the x squared term is the negative, right? So what does that do? What does that do? I've already told you earlier. See if you can remember. The signs are reversed. Oh, look at that. Now, what that is, you see the blue hyperbola, it's not a left and right hyperbola. Now it is an up and down one. You see that? But the thing is, it has the same centre. It has the same centre point. And the curve is an up and down one. Now, this is the point I want to make. The asymptotes are the same. The asymptotes are the same. It's just that the curve is different. And the other thing to notice is that B, that's the term there I've just highlighted under the y squared term. That's 12. So therefore B is root 12. So now in this case the vertex of the up and down hyperbola is root 12 units vertically, up and vertically down from the negative 4 y coordinate of the centre. Do you get that? Yeah, it's very important to get that, okay? Very important. I think we're nearly finished. Oh, yes, we are, thank goodness. So it's all good. We're all smiles. We've managed to do ellipses, and we did them jolly well, even if I do say so myself. And we did hyperbolae, and we did a great job. And look what the little smiley face has got to say for us. Hey, hooray today. So, there you go. Wow, well, what about the next exciting instalment? We'll have to wait for that. Okay, see you all later.